Hello, everyone. I'd like to thank you for attending my session. I'll be talking a bit about phased arrays and some of the challenges around phased arrays, and specifically interconnect design for interfacing between transceivers and system controllers and antenna elements in phased arrays. So I am Zachariah Peterson. Everyone calls me Zach. Worked in academia prior to coming into the PCB industry, and some of you probably know me from my work on the Altium blog, also a member of several professional societies. But in this particular presentation, we'll be talking about phased arrays, and I'll go over some of the points here surrounding PCB stack-up, things like layer arrangement. Those are two of the important areas where successful design will lead to some of the best phased array performance, as well as the best transmission line performance. So we'll talk briefly about the different types of transmission line options, but as you get to higher frequencies, coplanar lines start to dominate. Now, one of the big challenges in phased array systems is the number of antenna elements. It just keeps going up. And this is creating a challenge in terms of getting signals into antenna elements, and it is requiring via designs that can support wideband signals, or that can operate in a narrow bandwidth, but at very high frequencies. And so we'll look at some design options for that as well. I'll also run over some of the challenges in different types of beamforming. So for those who are familiar with phased arrays, you're probably familiar with the generic analog phased array, but there are also digital beamforming that is performed with phased arrays, and then also we have hybrid beamforming that is performed with these antenna arrays. And antenna location, or co-location rather, is also quite important, and that creates many of the design challenges that we'll look at in this presentation. So co-location is not rigorously defined, at least not from what I've seen in the literature, and I've even been told by folks who work in this area that there is no strict definition. And the co-location is important because it does determine the resolution of the system in 2 dimensions. So first, let's look at just kind of a broad view in the progression of these systems. The big trend in phased array design has been towards more emitters and higher density of emitters. The reason that we go for more elements is because we would like to get the higher resolution. And so this has driven a shift from older style radars that have not the best resolution to radars that could conceivably be used for imaging and have very fine spatial resolution. They generate a lot of data in the process, but they could conceivably used for very high resolution imaging, as long as you can get all of the data out. Now, more elements also gives you more gain, which means you have more power being broadcast along a single direction that goes hand in hand with resolution. And when you have more elements, you can accommodate more streams coming into the array via spatial multiplexing. And most folks will probably know this as a version of multi-user MIMO. And in these 2 systems that I've shown here in this slide, the lower left is your generic radar system. This is actually an NXP design, and I like to show this just because it shows some of the trends in radar. Here in the lower left side on the one layer, you have the radar transceiver connected directly to the antenna array. You got the transmitting and the receiving array on the opposite sides. You have some dummy antennas here, and you essentially just have 3 and 4 transmit and receive elements. The trend for smaller systems that can get to higher resolution and have higher gain is to incorporate many more elements and many more transceivers as well. as much as we would like to fit maybe, let's say, a 10 by 10 array into a single chip is just not possible to do that. And so what we tend to have is multiple chips that are cascaded or orchestrated in some way in order to produce the phase offset between all of these different antenna elements that then produces our beamforming. And so on one side of this PCB, you have a bunch of chips here lined up in this 2x4 array, and then on the other side you have all of these antenna elements lined up, and these are then connected with a via. And so this via design here is really essential to get the signal from these chips into these antenna elements. So what happens once the signals get to the antenna elements? Well, we then can perform beamforming by setting the phase between different signals that are sent to each of these elements, and this is well known as analog beamforming. So the maximum angle has some limitation depending on the wavelength and free space and then the size of the element. The distance between the elements has to meet a certain condition in order to actually reach that theoretical maximum scanning angle. But the point here is that all of this can be controlled in terms of the broadcast angle by controlling the phase of all of the signals that are sent to these elements. And that tilt can be done actually in two angles, in azimuth and elevation, within this array. So we essentially have a 2D scan here. Usually this is presented or talked about in terms of a 1D scan or in terms of a single angular scan, but you can actually do this in 2 dimensions. And you can get varying levels of resolution in each dimension. There's also digital beamforming. And digital beamforming essentially involves mixing the amplitudes and phases of incoming bit streams. And it is easier to compensate for known phase mismatches just by delaying these bit streams by certain amounts, whereas in the case of analog beamforming, I have not heard of any kind of on-chip calibration procedure that could then compensate for a phase mismatch, at least not extreme phase mismatches. There is a newer chipset by one semiconductor company that does do a calibration procedure and can compensate for small mismatches. But one of the moves towards digital beamforming, specifically in some of these applications like automotive, where they want to do high antenna element count radars, is that this is more scalable. And so there's a bit of a fight here between analog beamforming and digital beamforming. But in any case, you still have all of these individual elements. You're going to have individual chips here that then have to route all of these signals into the antenna elements. So you have all of the antenna elements on the same layer, and at some point, as you increase the number of antenna elements, you just don't have room for any of the chips. And so you then have to draw these interconnects as coming from these chips on the back layer or on an internal layer, and then through a via up to the top layer so that you can actually broadcast the beam and do beamforming. There is also hybrid beamforming, so this is, as its name suggests, a mix of digital beamforming and then analog beamforming. So you have a digital beamforming system here that then sends those different mixed bit streams off to an analog beamformer, which then provides some phase delay between all of the different elements, and then that allows essentially this portion of the array to broadcast at one angle or another, and then that beam is going to depend on the phase mismatch between the signals sent to those different elements. So you're essentially combining digital beamforming with analog beamforming to control this signal broadcast direction. And so if we kind of look at this layout concept, this is a layout concept that I've seen frequently in my work on radars. And the layout concept essentially works like this. You have your transceivers in one area on the back layer. Obviously, you'd like to make this system as small as possible, and so you then cluster all of the antenna elements on the top layer. You might have the controller here on the top layer or on a separate board. This controller could, I've drawn it here on the top layer, but it could also be on the back layer. Or if it's on a separate board, its control signals are being routed into all of these transceivers, possibly through an internal layer or through the back layer. And then you have the feed lines going into each of these antenna elements, and with some meandering in order to enforce some level of phase mismatch. So depending on where these different antenna elements are located, you could route straight into some of them, but in order to maintain phase mismatch, particularly with analog beamforming, you then have to apply meandering to some of these antenna elements that are closer to each of these transceiver chips. And so what we've actually done in some of the designs that we've had to deal with is we've actually had the controller on a separate board. We've had half of the transceivers on the top layer, half of the transceivers on the back layer in an orthogonal arrangement, and then we've sent those feed lines to all of the different antennas and actually been able to maintain phase matching quite well. But that is a really challenging type of layout because most of the board space is just dedicated to routing those feed lines between all of the transceivers and the antenna elements. Then, of course, in the stack up, you've got power on multiple rails. You're going to have multiple logic levels because these transceivers are operating at 1v8, 1v2, and probably at 3v3 for their main power rail. And then, of course, you got ground interleaved in between all of this. So these antenna boards can reach reasonably high layer count. 8 to 10 is common, could go as high as 16. The largest that we've done is 16 layers. So all of those transmission lines that you have to then route between all of these transceivers and then all of these elements, they have to be very precisely designed according to the stack up that you've used in the board. In this type of design where you have the antenna elements on one layer and then the transceivers on the back layer, you tend to have a hybrid stack up so that you've got like a low loss PTFE material on the outer layers. Then the inner layers can usually just be like an isolo low loss laminate or even just standard FR4 if you're talking about separation between the power and ground rails. But in any case, you will then have to design those transmission lines to take account of all the possible loss mechanisms that can exist in this system. So of course we have the skin effect, and I say this is incomplete because it has to include a roughness factor, which then enhances the skin effect and makes that skin resistance larger. And then you have to, of course, account for the loss tangent for these for the materials that you're using in your system. I always like to present this model because it is very useful if you are going to be doing any kind of analytical calculations. And so I would refer readers to this paper that I've cited here at the bottom of the screen. This IEEE paper does a really good example of showing how to actually use S-parameter data to get the parameters in this model so that you can then do transmission line design within a causal framework. So the other challenge here in these systems is to have a wideband signal launch. So that signal launch could come from a connector, but if you're dealing with transceivers, you're actually using the same signal launch going into an internal layer or possibly onto the back layer in order to get that signal from the transceiver into a transmission line, which will then carry that signal off to its destination, which will be one of these antenna elements. So this particular set of equations is provided by this author who I've cited down here at the bottom. He also came up with this image. For these equations are telling you the impedance and cutoff frequency pair for a given set of diameters for the ground via arrangement here, and then the diameter of this signal via to which the connector or the component will be attached. So we've seen these same types of signal launches being used that would normally be used for connectors, also being used appropriately for transceivers, specifically transceivers that use BGA footprint. So you essentially have the pad here connected to the BGA. This is typically a blind via going into the internal layer, and then it goes off towards the antenna elements. So another important aspect here that I mentioned earlier is that many of these designs are being done with coplanar waveguides. Coplanar waveguides, as I'm sure some folks in the audience know, can support coherent modes that can propagate along the waveguide and then reach some other element in the system, whether it's an antenna or some other component. In any case, we like to have, or we would generally prefer to have something like we have here in the 1 gigahertz row, where we have TEM propagation. This is essentially just a constant amplitude across the entire length of the interconnect. However, if you're doing something like we've done in a couple projects involving slot emitters from substrate integrated waveguides, this non-TEM propagation can actually be very useful. The reason it's so useful is because you do have propagation of a coherent wave with a very specific wavefront or pattern here as outlined in these graphics. And then you can use that to then excite a slot to then emit very strongly. So it's not that you can never have or shouldn't ever have non-TEM propagation. In some cases, it's actually useful. But generally, if you're dealing with wideband signals, you'd like to have TEM propagation. And so what that does is it actually pushes the size of these coplanar waveguides to be much smaller as the frequencies in these systems get pushed to much higher values. So you can actually see that here in these values, or in these S21 plots for a set of coplanar waveguides that can be reviewed in this paper I've cited down here at the bottom of the screen. So in these coplanar waveguides, as we have a physically larger structure, the mode structure then gets pushed to lower frequencies. And so when we have these mode excitations happening here at specific frequencies, what we then see is a lot of power loss at those specific frequencies. And once we get down here to this VL equals 400 microns line, so this is the via, the lateral size of the coplanar waveguides is defined by the via location, and then also the via pitch. Once we get to these numbers here, you can see here that we can actually push the bandwidth of coplanar waveguides very high. So definitely high enough to accommodate 77 gigahertz radar and even higher frequencies. The challenge is that you're starting to get right up to the limit of what you can reliably manufacture with standard processing once you start creating structures of this size. And then what happens is you end up having a power loss curve that can be calculated from this S21 data. So this is the corresponding power loss data. But from this data, you can then define a bandwidth for this structure. So just over here on the left, we have a structure that we have designed in the past using 30 mil Rogers 4350B laminates, and with 2 millimeter via spacing, you have reliable 50 ohm impedance propagation up to about 42 gigahertz, and this is going into a an SMD connector here on the right hand side. This particular application was used at 6 gigahertz, so you might say it's a little over designed, but this particular design does work well at that frequency as well as at higher frequencies, and is very reliable. So this should illustrate some of the challenges in working at these higher bandwidths, because eventually all of this is going to then continue to shrink to the point where you start running up against manufacturing limitations. So the other thing about via transitions, and the thing I always point out to folks who are trying to use via impedance calculators, is that via transitions can also have those resonances. And most via impedance calculators are incomplete. What I mean by that is that they simply can't calculate any of this resonant behavior that occurs due to wave propagation within this structure. So just as an example here, I'm showing in return loss data for a via that's designed to operate right at about 68 gigahertz, and you can see here that we've got decent bandwidth here, right around 68 gigahertz, as long as we don't need too large bandwidth, and we've got really good matching right here at 68 gigahertz. So you can see here we get between 25 and 30 dB return loss in this structure. And so designers need to work with or select the via dimensions, both for the stitching vias as well as the signal via. They need to select a pad and anti-pad size. Do they remove or do they keep the non-functional pads? And eventually what's going to happen is these stitching vias are actually required in order to hit a 50 ohms impedance target, or any other impedance target for that matter. So we can see the effect of the stitching vias if we look at some of these plots from Symbior. Here, the via impedance with no stitching vias initially looks inductive. So here in green, you can see the anti-pad. We've got the feed line coming in and going out in red, but then we actually have no stitching vias around this, and you can see what happens to the plot here. If you're above a couple of gigahertz, this structure is not going to support much signal propagation up to high frequencies because the impedance starts going up and eventually gets too large. Once we add in some stitching vias, depending on where those stitching vias are placed, you could actually get the total opposite effect. And so what this shows is how sensitive these via structures can be to capacitive loading. You could actually have the total opposite trend with the impedance falling very low and then becoming inductive again. However, we would always like to get to this kind of ideal result within the frequency range that we're working in. So this particular via design would work great within a pretty broad bandwidth and could support lower frequency radars if needed. So here we would want to aim for 50 ohm impedance right around the area that we're working in. But this is a really nice broadband via transition that we might need to use. Now, one thing that we could do is, of course, just say, forget about trying to do broadband, we're just going to go narrowband. So in this case, there are some tricks that you can use to get a narrowband via plus feed line design to then get very high power to then transmit through this structure and then into the component or element that you want to use. So you start with a wideband signal launch, and then you get over to your via structure, and then in this trick I'm going to show in the next slide, you actually have a short section of feed line coming off of your via transition and then going to wherever you want it to go. It could go to a component, or it, as I've shown here in this graphic, could go to an antenna. And so just by tuning that feed line up on the top layer, you can actually control where these peaks sit in the S11 spectrum. So that's what I'm showing here in these graphs from Symbior. And you can actually get really nice matching right at 77 gigahertz. Now you'll notice here that we only get to about negative 12.5 dB return loss. However, if we just readjust this anti-pad shape and then maybe add in some more vias, we can actually get even better matching right around 77 gigahertz just by tuning this feed line size and then tuning the via properties as well. So more vias in general is going to give you better matching. It's going to give you a higher Q value. So maybe this isn't the best approach for trying to get to a broadband via transition at these frequencies. So just to conclude here, these signal launches typically use blind vias, and the same goes with via transitions. But as I outlined earlier with the challenges with phased arrays, scalable phased arrays might require through holes. So there's a challenge here in designing those through hole layer transitions so that you can transmit broadband signals into those emitters if that's what your application requires. Of course, you could use cables and connectors, but really you need to eliminate those if you want to get a very compact system. So into this mini gigahertz range, it is a persistent challenge, and it does require quite a bit of simulation and optimization in order to do it properly. And there is actually quite a bit of literature about it, and I would encourage anyone who is working in this area to learn about via transition design so that you can operate in the high gigahertz range. All right, thank you, everybody.